Greetings, welcome to Lab 3, Part 1, Working with the Normal Distribution. So in this particular chapter, the way things are going to work is we're going to have our course videos and the lab as the same thing. Kind of nice, they're not going to be separated out, make life a little bit easier. So what's going to happen here is we're going to work through a variety of exercises from the textbook to illustrate some of the key ideas from the textbook and to also show you how to use RStudio to do the calculations that are necessary for it. So let's go ahead and get after it here. We're going to start off with problem 3.2 from the homework, and what I've done is I've gone ahead and opened up RStudio and got an RMD, a markup file or markdown file all ready to go to get us going in this. Okay, so this is lab 2. Because we started lab 0, so we got to count 0, 1, 2. Okay, so this one is actually lab 2. So the problems that we're going to be doing in this lab are going to be coming from page 149. And I'll do a separate video for each of the exercises. And obviously you're watching this one. This one was titled Exercise 3.2. Okay, so quick thing from the last lab, you may still have all of these data sets left from the last one. You might want to get rid of those because remember we went through a lot of effort to make sure we didn't have to have all those data sets sitting in there. We put it actually into our RMD so it was all self-contained. So if you press on the clear button over here, it's going to say, do you want to get rid of all that stuff? And I say, yeah, just get it out of there. Okay, so that'll be gone and you won't have to worry about it. All right, kind of unclutter the situation a bit. Okay, so first thing that we're going to want to do here is read the problem. It says, what percent of a standard normal distribution n of 0 by 1 is found in each of the regions? Okay, and it says, be sure and draw a graph by hand. So I'm assuming you've got your textbook open in front of you and that you have read this section. If that's not true, then pause this video and go back and first of all finish the assigned reading, and then once you finish the assigned reading, get RStudio and everything opened up to like what I've got going on here. Okay, so let's go back over to the whiteboard and let's go see what they are asking us to do here. Okay, so let's see, let's come back over here. So let's take a moment before we go any further into this and talk about what we mean by a normal distribution. So from the reading, you hopefully got that a normal distribution is, the name is apropos because it's really often that we come across the distribution of our data being bell-shaped, symmetric, unimodal. It's a very common occurrence, happens in lots and lots of different types of data. And so we'll see as we move through the class that it's going to be really common that we're going to get this sort of, I'll kind of do my best job of tracing over it here, this sort of bell-shaped curve. Okay, now a couple of very interesting features about this bell-shaped curve, and that these 2 points right here are exactly one standard deviation away from the mean. In other words, we know that this distance from here to here, that distance right there, is a single standard deviation. Remember, the character for standard deviation is given by a lowercase Greek s or a sigma. So that's a single standard deviation, and then that distance right there is also a single standard deviation. So hence we get the mu plus sigma and mu minus sigma for those endpoints. Now notice that it's labeled that these are the points of inflection. Now what do you mean by a point of inflection? Well, an inflection point means, I'll come down and draw another bell curve here for you, is that notice that I'm hit this piece right here that I just drew, this rather fat chunk I'm drawing, that could be inferred to be concave up. If you think back from your parabola experiences, that's concave up and that's concave down, okay? Where we switch concavity from being concave up to being concave down, notice that was at this point right here. Let me change colors on you here. So now notice here this part of it I am concave down. So that concave down point where we swapped from being concave up to being concave down, and then the same thing down over here, those points right there and right there, those are referred to as a point of inflection. Wherever we change concavity, we call that an inflection point. And what happens is that's where we know from just our rough drawing, we know that that is exactly one standard deviation either side of the mean. Now, of all of the normal distributions that are possible, by the way, before I go on to that, let's just remind ourselves quickly of the notation right here. This is the shorthand to tell us which normal distribution we're working with. We use a capital N to say, hey, it's normal, and that the mean is given by mu and the standard deviation is given by sigma. So just to make sure, preview of coming attractions, both of these values right here, those are going to be what we refer to as parameters. And those come from what are referred to as the population. So those are population values. So this is actually a population model, is one way of thinking about it. Is that this is a model that we're using to describe an entire population. Okay, so let's take a look at one of the most popular versions of the normal distribution, and that one's called the standard normal. So let's go ahead and you're gonna have to get used to freehanding or drawing these things, because part of each of the assigned problems is going to be to actually make a sketch of the situation. So you're going to want to get really good at just drawing yourself these, turtle shells, okay? And so a standard normal distribution is a particular normal distribution where the mean is going to be 0 and the standard deviation is going to be 1. And as we'll see in the not too distant future here, in just like a minute or so, is that this axis right here, the horizontal axis, is going to be given by z, and then the vertical axis here, this is going to be given by what's referred to as density. Don't lose too much sleep over density. It's basically frequency. It's how often things occur. It just happens to be its modified frequency to make sure that the area under this curve remains 1. We have to have exactly 1 for the total area underneath the curve. Again, you did your reading, so hopefully that all makes sense to you. Okay, so back here at the standard normal, we know that we're centered here at 0, and at either side of 0 at our inflection points, we're going to be 1 standard deviation above and below. So that means that this is going to be at 1, because look, our standard deviation is 1, and this is going to be at -1. All right. Okay, so we'll be drawing a bunch of pictures. We'll be making a bunch of pictures in this homework assignment, because every one of them that we calculate the area under this curve for, we're going to want to start off with drawing the picture. And for the first set of problems, they're all going to be given by the standard normal, so the variable involved is going to be z. When it's not a standard normal model, then the variable will just use an x to indicate that that's the x-axis or the horizontal axis. Okay, so let's go ahead and work on part A here. Okay, so let's go ahead and get ourselves a fresh window here. I'm going to go ahead and grenade this one, get it out of here. Okay. And so on part A, again, this is from exercise 3.2, okay? So on part A, they ask us to find out what percent is such that the z is greater than -1.13. Okay, so to start off this problem, do not pass go, do not collect $200 until you've actually done a reasonable sketch of a standard normal. All right, you notice mine aren't great, and that's okay, because we're just trying to get an idea of what's going on here. So we know that since this is the standard normal with a mean of 0 and a standard deviation of 1, that it's centered at 0. And we know over here at this inflection point that that's at -1 right there. Okay, so that point right there is roughly at -1, which means our z value, which is -1.13, that's going to land right about there. So that's at -1.13 roughly. Now what do they want? Well, they want the z values to be greater than 1.13, right? Okay, so what they're asking for is this area in here. They want all of this shaded region that I'm in here shading right now. They want that area right there. And in fact, to do it legit, to do the math, you actually need to use calculus to find out what the area under that curve is, and that's non-trivial. That's not a simple thing to actually do. So, but we don't have to do that, because we have the capacity to do that with either using RStudio or using tables. Now, I do not recommend you use tables. I recommend that you use RStudio for doing all of this. Okay. All right. So, how do we go about figuring out what that value is? In other words, what they're asking for us, that area, that proportion, that percent, we're going to notate that as what is the proportion of values, what is the probability of seeing, what is the percent of values of z's that are greater than -1.13. That's what that notation means. It's kind of like function notation. You're inputting the argument, hey, I want to know what proportion, P for proportion, probability percent, of z's are greater than negative 1.13, and that's what that shaded red region is right there. Okay, now how do we get RStudio to do that? Well, let me go ahead and switch back over to RStudio here, and I'll show you the command, and then we got to come back to the whiteboard for just a minute and talk a little bit about how to actually get it to work. So let's come down to the console for a minute and put in a question mark and put in pnorm. And if you do that, you should get the same help window that I have sitting over here. Actually, I had it sitting already, but that's the tool. Pnorm and Qnorm are going to be the two that we're going to want to use. These two commands right here are going to be the ones we're going to use really often. And notice they're very similar to each other. The only difference really is the P or the Q, whether we're looking for a probability or if we're looking for a quantile. More about quantiles after this problem. That's not in this video. Right now we're just looking for probabilities. Okay, so let's go back here and notice what it's asking for. So when we're doing pnorm, it wants to know what is the value. Give me what is it that you're looking for. What is the value on your axes? The default is that the mean will be 0 and the standard deviation is 1. You can change those if you want to. And it says lower tail equals true. So notice that RStudio and R gives you areas under a standard normal curve just like the textbook table does. They're left-tailed or lower-tailed tables. In other words, the area comes from the left, all right? So there's a couple of different ways we can get RStudio to do this for us. So let's go back to the whiteboard here for just a minute and let's talk a little bit about how we can get RStudio to do this. So one way is we can say, all right, well, this is pnorm. So I want a probability from a normal distribution. My value that my mark in the sand here is at negative 1.13. My mean is 0. My standard deviation is 1. You don't have to put the mean equals or SD equals. You can just put the numbers there and that works just fine. And then I can come in and put in, I'm going to add a room, so I'm going to come down below here. I can put in lower dot tail, actually that all has to be lowercase, is equal to false in capital letters, okay? Now I got to be honest with you, I don't ever do it this way. I always forget, is it left dot tail, lower dot tail? I'm always having to look at the remind myself using the help, and so it becomes rather confusing to do it that way. If you notice in the book what they said was, well look, if you take and you come over here and you subtract off this blue area right here. If I take that blue area and I subtract that off of the whole thing, what's going to be left is the red area, isn't it, right? So in other words, I can find the red area by simply coming in and saying, well, take 1, which is the area of everything, that's the red and the blue combined, and subtract from that the area in the blue. In other words, come in and subtract from that pnorm, negative 1.13, comma 0, comma 1. And notice that this blue corresponds to that blue area right there. I subtract that from 1 and I'm going to get back the red area. All right, so let's go ahead and go give that a try. Let's get into RStudio and actually see what it does. Now remember, we're going to have to open an R chunk because we're in an R markdown file to actually get that to work, okay? So from here, let's go over to our chunks. Let's go insert an R chunk, and then let's come in and put in the command that we want. So we want what? 1 minus, timeout, sorry about that, you guys, I need to do something first. This is problem A, so let's put an A dot here with a couple spaces so that we know that this is the problem we're working with, okay? In fact, we should probably put in the actual question, which was what, z greater than negative 1.13, okay? Yeah, sorry, I get a little ahead of myself. I was getting excited. I wanted to do this, okay? So we're going to go pnorm, and let's see, negative 1.13, comma 0, comma 1. All right, so let's go ahead and run just that R chunk to see what it gives back to us. So we'll run the current chunk, and bada bing, bada boom, there we go, down to the console. Remember, when you run an R chunk, it executes it in the console for you. It shows us that it's about 87% of the z values fall above negative 1.13. Now go back to your drawing for just a second. And you go back to your drawing. Well, yeah, looking good. I agree. That looks about that amount over there, right? I mean, it looks to me like if I had to make a guess, I would have guessed about 80% or maybe 85% of the data fell in this piece right here, okay? All right, so something, before we move on to the next problem, just a quick something I want to remind you of is that the length of this axis, the z-axis, it's heading up here to positive infinity, and it's heading down here to negative infinity. But as you can see already by my drawing, the further you get away from 0, the less area there is under the curve. In fact, the area gets smaller and smaller and smaller the further out you go. But it's non-zero. There is still some area out there. It just could be, 15 places after the decimal point before you pick up a non-zero number, all right? When I took this class, it was interesting. My professor said, this is the case where it's much better to be the guy who's laying the carpet than it is the guy who's laying the baseboard, because the carpet's got a finite value. There's one square unit you could think of carpet to be used, but there's an infinite amount of baseboard to be used. Kind of a mind blower. All right, anyway, let's get back to the problem at hand. Okay, so that was part A. We're going to pick up the pace here a little bit now, and let's go do part B. So part B, and then let's go back. Oh, first of all, let's go see what the question was. Go back. So let's see. Part B. Hang on for a sec here. I got to flip my page. Z is less than 0.18. Okay, so Z is less than 0.18. That's what we want to do, not X. We wanted Z this time. We'll get to X eventually, but Z for the moment. Okay, so we're going to be inserting an R chunk, so I'll just go ahead and do that and leave it waiting for us. And then we're going to go back over to the whiteboard real quick and do our drawing, all right? So back over to the whiteboard. In part B, we got to draw that, okay? So let's go ahead. I'm going to open up a fresh whiteboard here. Put that in. Okay, great. So we've got a fresh one here. Got a freshie. And so this is going to be, there you are. This is 3.2 part B, okay? So what we're looking for here is we want to know the proportion or the probability of seeing Z values less than 0.18. Okay, so we know again, since it's a Z, that's a dead giveaway that the model is n 0 by 1, all right? So let's draw ourselves a standard normal distribution here. Ooh, that's a beautiful one, I'll tell you. So we know that the mean here, we know mu is equal to 0, and we know sigma is equal to 1. This is our z-axis right here, and they're looking for z's less than 0.18. So 0.18, that's going to be about there-ish, kind of, sort of, okay. And so let's go ahead and shade in the part that we're looking for. So it's going to be this part over here, isn't it? This magenta. Beautiful shading that we've got going here. So that magenta region is what we're looking for. Now notice we're in luck this time because they're asking us to find the area in a left tail. And since they're asking us to find the area in a left tail, that means I can use the p-norm directly. So I don't have to do the 1 minus because I'm the stuff. If it's in the left tail, no 1 minus. If it's in the right tail, then you got to do the 1 minus. All right, that's a good rule of thumb. We'll write that down here for you in just a second, but let's finish this. So this is p-norm, and then it's going to be what? Well, let's see, this value right here was at 0.18. That was our cutoff right there, okay? So, and this value right here, of course, that's at 0 at the mean. So this is p-norm of 0.18, comma 0, comma 1. I'll be honest with you, if you leave off that 0 and 1, those are default values, and R will give you the calculation without doing that. But my advice to you is just get in the habit of always putting the mean and the standard deviation in there, and you won't forget to do it when you need to. Okay, so let's go back to RStudio. So in our R chunk here, we're going to put in p-norm. We're going to put in 0.18, comma 0, comma 1. All right. And again, let's go ahead and just run that chunk to make sure that makes sense. Looking good, yeah, slightly more than 50%. That makes sense because we were just above the mean, and we know that in the case of a unimodal distribution like this, that half of the data falls above the mean and half of the data falls below the mean, right? Because it's the mean and the median are identical here. Okay, cool beans. All right, so we got part B. Let's get on to part C. So part C, we've got z is greater than 8. Okay, and we'll go ahead and put an R chunk in right away, although I already know the answer before I even do this, but I'll explain that in just a second. So insert an R chunk, not run an R chunk. We don't have one there to run yet. There we go. Okay, so let's go back to the whiteboard and let's go draw our problem. Okay, I'm going to go ahead and grenade this one. Get a clean board out of this. And so let's see, we are going to have 3.2 part C here. So here is our standard normal curve with the mean of 0 and the standard deviation equal to 1. And remember, again, this is our z-axis. All right, let's go back and talk a minute again about that inflection point idea. So this point and this point roughly are one standard deviation above and below the mean. So that's roughly at -1, and this point right here is roughly at +1, okay? So it's a -1 and a +1. So this distance is at about 1. So if I go out another one of those 1s to about here, that's going to be at 2. And I go out about another one of those distances, and that's going to be at 3. And the same thing down over here in this direction. That's going to be roughly at about -2, and that's roughly going to be about at -3. And so what you can see is that once you get more than 3 standard deviations above or below the mean in a normal distribution, that you pretty much have run out of area. That the area is getting really small at that point. Now, what did they want? Well, I'm going to put a little break in the axes because I got to get way out here out to 8, don't I? They want to know, in this case, what is the probability of z being greater than 8? So the area that I'm going to get out past 8, well, I mean, I can't even draw it thin enough to actually represent it accurately. It's less than the thickness of a line. So that area, for all intents and purposes, is going to be 0. In fact, it's going to round off to 0. But we'll go ahead and do it anyway. So what are we looking for? We want the probability of z greater than 8. So it's a greater, which is an area to the right, so we're going to have to do what? A 1 minus, aren't we? So that's going to be 1 minus p norm. And let's see, our value was at 8, our mean was 0, our standard deviation was 1. Okay, so before I go back over to RStudio to do that calculation, one more time about what's going on here. Okay, so if it is a right tail, in other words, when you draw your picture, and you get a right tail area, then that means that you're going to do 1 minus p norm. And it's going to be x by mu by sigma, okay? If, on the other hand, it is a left tail, if it's a left tail, then that means the area is over here on the left side, right? So if you got a left tail, then in that case, what you got going there is you just use p norm. You don't do the 1 minus of x by mu by sigma. Sorry, my handwriting's not that great when I'm doing this on these whiteboards. It's only marginally better when I do it on a full-size whiteboard, but it's definitely a little sloppier on this pad. Okay, so let's go ahead and get back into RStudio and let's go calculate it. I said I think it's about 0. Let's see if RStudio agrees with me. So I'm going to come in and go 1 minus p norm, and I'm going to put in an 8, 0, 1, and then let's go ahead and run that chunk. And it comes back out 6.6613338 E negative 16. So what in tarnations does that E negative 16 mean? Well, that means that there are 15 zeros before you get to your first non-zero number. Let me go back to the whiteboard real quick and let me show you what the heck that meant. I'm just going to go to 1 decimal point. What that's saying is that that's basically, for simplification here, I'm just going to say that that's 6e negative 16, okay? Or excuse me, 0.6. Let me check, make sure I'm writing that down right. I want to make sure I'm not lying to you here. No, 6.6, yeah, so it's 6.6. So we'll go 6.6. I'll run it out at 6.6 there. So it's 6.6e negative 6. I know I'm not rounding correctly. Don't worry about it because this is all just academic. We just want to see what's going on here. And so that was negative 16. Yes? Yes. Okay, cool. All right, finally got everything transferred over here correctly. So that's approximately going to be, I got to move that decimal point 16 places to the left. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 6, 6. Okay? Now, most reasonable people would round off at about 3 decimal places. I'll let you round off here. Let's go say 6 or 10 or whatever. What you can see is this is what approximately 0, isn't it? So we don't put exactly equal to 0. We put in approximately 0 when we're writing it by hand. Or you'll see in some textbooks they'll put 0 and they'll put a little plus above it. They say, well, it's not 0. It's a little more than that, but for all intents and purposes, it's 0. Okay? So highly unlikely that you're going to see C values greater than 8. All right, let's get on to the next problem. Let's go back over to RStudio here and go type in part D. So let's put in D. And in D, they ask us to give the absolute value of Z less than 0.5. Okay, so they want, back up here, the absolute value of Z less than 0.5. Okay, so quick reminder, you may or may not remember how to deal with an absolute value inequality. But I'll tell you, when they do this to us, it's a very commonly used notation. This is actually the trap notation. When you see an absolute value of Z being less than 0.05, that means that that number is trapped between a negative value of negative 0.5 and a positive value of 0.5. And I promise you on quizzes, exams, etc., that I would not give it to you in the absolute value notation. I'd use the notation that I've put right here, okay? So if you're not familiar with that, don't sweat it. I'm going to give it to you this way, okay? But you do need to know it for the exercises because there is a problem like this in 3.1 that you'll need to be doing, okay? So let's go insert an R chunk. And now what we got to do is go back over to the whiteboard and figure out actually how to do that calculation. So let's go do that. Go ahead and give ourselves a clean whiteboard here. And let's see, how do we go about doing that? All right, well, let's draw the picture first. As with all of these 3.2 part D, how does that look? I mean, what is that going to look like? All right, well, we're going to again have a standard normal distribution. Here's my Z. This is n of 0 by 1. We know that we're centered here at 0. That's our mean. Okay, and so what we want is the proportion of values of Z's that are between negative 0.5 is less than Z, which is less than 0.5, right? So what proportion of values actually fall in that interval? Okay, so we know that right here and right here, roughly on my drawing, are plus and minus 1 standard deviation. So going about a half a standard deviation either side of it. So we're roughly looking for the shaded region that is trapped between those 2 points that I just marked. In other words, this is my shaded region in here, okay? That's what I'm looking for. Where we know that these endpoints are at what? Well, they're at 0.5 and negative 0.5. Okay, so how do I do that? Well, remember, RStudio, as within most tables that you use, is calculating the area from the left. So let's think about that for a second. Let's come in and think about what would this blue shaded region be right here? How would I calculate that blue shaded region? Well, the blue shaded region right here, that would be found by coming in and going, well, P norm of negative 0.5 by 0 by 1. In other words, that would be that entire blue area there. Now, what about the red area? Well, let me tell you that I'm going to change this a little bit. That if I wanted all of the red area, everything, it would look like this. So this thing that I'm outlining right here, if I want that area right there, what would that look like? In other words, I want the blue area and the red area combined. Well, the outlined area is going to be given by P norm positive 0.5 by 0 by 1. And so hopefully you see the trick there. What we're going to do is we're going to come in and we're going to do both these calculations. We're going to calculate the area of the big red piece, this whole thing, okay, everything here. and then subtract off from it the area of the blue piece. And when we subtract off of it this blue area down here, all that's going to be left is the actual piece that we wanted, okay? Which is the red piece right here. In other words, that'll get us to, let's go, I'm going to go green here just to get a different color, is it'll give us this piece. All right, so how do I actually do that calculation? Well, you come in and you say, all right, well then that's going to be the big chunk, which is, let me go ahead and stay color coded here. That's going to be P norm of 0.5 by 0 by 1. And then I'm going to subtract from that the blue area, okay? So I'll come in and subtract from that P norm negative 0.5 by 0 by 1. Hopefully that makes sense to you what I'm doing there. I'm taking the whole thing and subtracting off the little piece to get what's left in the middle, all right? So let's go back over to our studio and actually do that. Okay, so we're going to type in, we're going to need two P norm commands. So first put in the bigger one. So the bigger area is going to be P norm of positive 0.5 by 0 by 1. Not by 2, Mike, by 1. There we go. And then subtract from that the smaller area, which is P norm of negative 0.5 by 0 by 1. Okay? And so again, let's go ahead and execute that R chunk just to make sure that that's looking good. Well, it would if it wasn't doing a ROM. I'm sure you guys are probably out there going, you dork, you typed it wrong. Okay, let's try that again. There we go. Okay, so we get about 0.382924.9 is the area that resides in there. Okay, so let's just go ahead and check my knitting here real quick. I'm going to go ahead and save this, and I'm going to knit what I've done so far so I can take a look at my file. And so as with all of our homeworks, the labs start off our homework because they show you in the lab, the whole purpose of the lab is to instruct you how do you get our studio in our case to actually do the work what we want it to do, okay? So same thing here. So the next video when we come back in is going to be a continuation of problems from chapter 3 to show you more work on how to get going with R, okay? So I'll see you back here for the next video. Hopefully that helped. And again, please do not be shy about asking questions. If any of this doesn't make sense, post questions to the discussion board, and I'm happy to do more work video-wise and or on the discussion board to help you.